Good day everyone. Today my team and I will be presenting our machine learning project. For this assignment, we worked with three different healthcare datasets to explore classification, regression and neural network models. The three datasets are breast cancer dataset, the medical insurance cost dataset, and the hospital length of stay dataset. Our main goal was to understand how machine learning can improve healthcare prediction, support faster decision making, and help organizations plan resources more effectively.
In healthcare field, accurate prediction is extremely important. Doctors need fast and reliable method to detect disease. Insurance company need to estimate patient costs fairly, and hospital must plan resources based on how long patients are likely to stay. In this project, we applied machine learning techniques to three different problems. First is classifying tumors as benign or malignant. Second, predicting medical insurance charges based on lifestyle and demographic features. And the third will be estimating how many days a patient will stay in the hospital. Each data set taught us different concepts and helped us understand how machine learning can be used to support real healthcare challenges. Next, we'll move on to the XSDM methodology. For the breast cancer dataset, our objective was to classify tumor as benign or malignant. The dataset contains 569 samples and 30 features describing characteristics of cell nuclei such as texture and smoothness. To prepare the data, we checked for missing values, normalize the features to a common cell scale, and apply lasso feature selection, which allow us to reduce the number of features from 30 to 16. We also performed PCA to reduce dimension further. For modeling, we tested logistic regression, decision tree, and random forest. Among these, logical regression performed the best with an accuracy of around 97.4%. Next, for the medical insurance dataset, focuses on predicting how much a person will charge for insurance. This dataset contains 100,000 rows and 54 features, including age, BMI, number of children, region, smoking status, and income. We began by encoding categorical variables and normalization continuous features. Outliers were detected and handled to prevent misleading results. Using mutual information, we identified the most important features such as smoking, BMI, and age. We also created polynomial features to capture more complex relationships in the data. We trained several models, including linear regression, Richet regression, lasso regression, random forest, and gradient boosting. Richet regression achieved the best result with the highest R-square value and lowest error. For the hospital length of stay dataset, aims to predict how many days a patient will remain in a hospital. The dataset includes detail about patient demographics, diagnosis codes, medical tests, and treatment information. During data preparation, we handled missing data, encoded categorical variables, and normalized numerical features. We apply correlation analysis and random forest feature importance to determine which features has the stronger relationship with the target. Because this dataset contains complex patterns, we used to feed forward neural network to model it. The model performance was evaluated using metrics such as mean absolute error (MAE) and root mean square error (RMSE).
In breast cancer dataset, we focus on reducing unnecessary features to improve model performance. We use lasso regression, which automatically eliminates less important variables by shrinking their values to 0. This helps us to reduce the number of features from 30 to 16 and create a simpler and more efficient model. Additionally, we use principal component analysis or PCA, which combines correlated features into components. The first four principal components capture about 84% of total information in the dataset, which helps us retain the important patterns while removing the noises. For the insurance cost dataset, we use mutual information for feature selection. This method helps us identify which feature had the strongest influence on insurance charges, and we found that smoking, BMI, and age contribute the most. We also added polynomial features like BMI squared and age multiplied by smoking status to capture more complex relationships that simpler linear model might miss. These steps made the dataset more expressive and improved the accuracy of our prediction, especially for the individuals with higher medical costs. In the hospital length of stay dataset, we applied several feature selection techniques to improve the neural network model. Correlation analysis helps us remove features with very weak relationship to the target. Random forest feature importance allowed us to rank the remaining features based on the predictive usefulness. In addition, we engineered polynomial feature to capture interaction between factors such as age combined with diagnosis type. PCA was used to reduce redundancy in the dataset, which improved model training speed and stability.
Okay, next. For the breast cancer dataset, we developed three classification models: logistic regression, decision tree, and random forest. Logistic regression performed the best, offering high accuracy and a strong AUC score, which means it was very effective at distinguishing between benign and malignant tumors. Random forest also gave reliable result and was more robust than decision tree. The decision tree was the simplest model, but it tended to overfit, meaning it performed well on training data but not as well on new data. Overall, logistic regression proved to be most reliable choice due to its balance of accuracy, simplicity, and interpretability. As we see next, in an insurance cost prediction task, we focus on building regression models. After selecting features with mutual information and engineering polynomial features, we trained models like linear regression, ridge regression, loss regression, decision tree regressor, and gradient boosting regressor. Ridge regression provided the best performance, achieving a high R2R2 value of around 0.966 and a low error rate. Linear and lasso regression also performed consistently well. In contrast, the decision tree model had a high error and lower R-square, showing signs of overfitting. Ridge regression was the most stable model for this dataset because it handles multicollinearity and prevents large variations in the predictions. Next, for the hospital length of stay dataset, we built a free-forward neural network because it is capable of learning complex patterns in medical data. The network consisted of an input layer, several hidden layers using ReLU activation, and an output layer predicting the number of days. We used the Adam optimizer and mean squared error as the loss function. To avoid overfitting, we added dropout layers and used early stopping, which stops training when the model stops improving. We evaluated the model using MEE and RMSE, and the neural network performed well, showing that it was able to capture the relationships between patient characteristics and their hospital stay duration. Thank you.
Okay, next I'm going to present about the performance and analysis of the breast cancer. The breast cancer shows the overall strong results. Starting from the logistic regression, it shows the achieve an accuracy of 97.4% and the AUC score which is around 0.997, which makes the model most reliable. Meanwhile, the random forest also performs well with the strong precision and recall values, which is important for detecting the malignant cases. Meanwhile, the decision tree had the lower scores and shows the display which is overfitting. Through the bias variance analysis, we observed that logistic regression had low variance and generalized well. Meanwhile, the random forest provided a good balance and the decision tree had high variance, making it more unstable. Next is performance and analysis for the insurance cost. So based on the insurance cost dataset, it shows that ridge regression shows as the best model, which giving the highest R-square value and the lowest prediction error. Meanwhile, for the linear regression and lasso regression also produce a stable result as well. And for the decision tree regression, it shows an higher error, which pointed to the overfitting issues. So based on these bias variance perspective, the linear based models had a high bias but low variance, making them more stable and reliable. And the decision tree had low bias but high variance, which made it less suitable for this dataset. For the overall, the model improved steadily with more data and especially the linear models. The last part for performance and analysis is hospital stay. So the hospital stay prediction shows that the neural network deliver a consistent performance with low MAE and also RMSE values. So this also perform a regularization sweep to explore the bias variance trade-off. So starting from the low regularization, it shows that the model perform extremely well on training data but slightly overfit. Meanwhile, the high regularization shows the model underfit by failing to capture the important patterns. And lastly, a moderate level regularization shows that the best balance between training and validation performance. And overall, this result shows the best model can support hospital resources planning by providing reliable predictions.
In conclusion, for the breast cancer model was very effective and distinguished between benign and malignant tumors. LASSO and PCA help reduce complexity while keeping the important features. Logistic regression offer high accuracy and interpretability, making it practical model for potential clinical support. Overall, the dataset shows how machine learning can contribute to early cancer detection. Medical insurance dataset, we found strong connection between lifestyle factors such as smoking and BMI and the final insurance charger. Mutual information help identify the most important predictors and polynomial features help capture non-linear relationship. Feature aggregation performed the best overall. These results show how machine learning can be used to estimate insurance costs more fairly and accurate. Finally, for the hospital length of stay dataset, the neural network successfully captured complex relationship in patient data. Feature selection techniques like correlation and random forest importance were essential for focusing the model on the right variables. Regularization helped balance bias and variance, making the prediction more reliable. The model could help hospital manage paid staff more efficiently. Overall, all three datasets shows how machine learning can support real-world healthcare decision making.